Hello and welcome to Some Assembly Required. Today I'd like to talk to you about timing diagrams again, but this time I want to talk about something practical. So what are we trying to do? This is a test harness for the 6502 I'm building. What it has is just the CPU and RAM. No ROM, no IOs, nothing else. In order for this to be able to do anything, the whole thing is controlled by an Arduino Mega. So the Arduino Mega sits on the address bus and the data bus, as well as the control lines of the CPU. It is capable of disabling the CPU and then writing values directly into memory. So that's how we get our program to run into the memory. And it's also able to monitor what everything is doing. Now, you'll notice that one of the things this board doesn't have is a clock. The clock is provided by the Arduino. Now, obviously, we won't get a 14 megahertz clock here. We won't even get a 1 megahertz clock here. I will be very surprised if we manage to get a 100 kilohertz clock. But since we're talking about timing diagram, let's assume we can get any clock we want, even though that's practically not likely. So we're going to need two data sheets here. The first is the datasheet for the CPU. As usual, we're using the 65C02 by Western Design Center. The second datasheet is for the RAM. I'm going to be using the datasheet for the 62256, which is a 32 kilobyte RAM, mostly because that's the CPU used by Ben Eder in his 6502 computer on a breadboard project. This is my implementation. Ben's looks a little different, but it uses the same components. So what do we need for the project? Basically, we need very little beside connecting the CPU to the RAM. So all relevant CPU address bus pins connect to the address bus pins on the RAM, and all data pins from the CPU connect to the data pins on the RAM. Likewise, since the CPU indicates write by setting the read-write pin low, and the RAM accepts a write by having a write-enabled pin that is active low, we can just connect the read-write pin to the write-enabled pin. Pretty much everything else are control lines, which we will more or less skip at the moment. We will connect the clock to the CPU. You will notice that we do not connect the clock to the SRAM, as the SRAM chip has no clock. It is entirely asynchronous in operation. The question we're asking ourselves is that it? Are we set to go? And the answer, of course, is that depends. Looking at the CPU's timing characteristics, we can see that it has several modes of operation, and those depend on the voltage with which it works. So at 5 volts, it can handle 14 megahertz. At 3.3 volts, it can only handle 8 megahertz, and so on. Since we don't want to limit ourselves, let's start with assuming 14 megahertz clock. Which brings us to the timing diagram. We'll begin with the read operation. The read operation, these are these two lines, requires that the CPU promises to have the address set up within TADS after the falling edge of the clock. TADS is up to 30 nanoseconds. And then it expects the data within TACC, which is 30 nanoseconds, so that the data is ready within TDSR before the next falling edge of the clock. TDSR being 10 nanoseconds. Since the clock spends low 35 nanoseconds and then high 35 nanoseconds, everything needs to fit within 17 nanoseconds. Let's see if our SRAM can even do that. Here we have the read timing waveform. And we can see that from address being valid until the data is valid, we have TAA. And if we take the fastest version of the chip, the one with the -5, TAA is 55 nanoseconds, which are more than the 30 nanoseconds we need. Remember, the 30 nanoseconds here are a result of everything needing to be 70 nanoseconds, and this being 30 nanoseconds, and this being 10. So 70 minus 30 minus 10 leaves 30 nanoseconds for address to set up. Since that's not going to happen even with the fastest version of the SRAM, let's just assume that we will not be using the 14 megahertz version. So we'll just limit ourselves to 8 megahertz. As a byproduct, we can now run the CPU at 3.3 volts. One good thing about deciding on a CPU frequency is that we can now lock on to that frequency and mark it down on the timing diagram itself, so we don't have to look it up every time. So let's see what we have here. TPWL is 63 nanoseconds. TPWH is 62 nanoseconds, which means that the whole thing is 125 nanoseconds. So 125 from here to here. Good. Now, TADS, which is address setup time, is 40 nanoseconds. And TAH, address hold time, is 10 nanoseconds. So this is 10 and this is 10. Last one for our case, TDSR, which is read data setup time, is 15 nanoseconds. Now, I'm not going to write TACC because TACC is just the 125 minus 15 minus 40. With that out of the way, let's look at the timing diagram for the memory. There are actually multiple read timing waveforms for the memory. The first is when everything is constantly enabled, which means there is no trigger to begin read. As soon as the address becomes valid, a certain amount of time passes and the data becomes valid. So that's TAA. And we see that TAA is either 55 nanoseconds for the -5 version or 70 nanoseconds for the -7 version of the chip. Which one do we need? Well, 40 and 15, 55, and 25 minus 55 is 70. So right now we'll assume we're using the 70 version of the chip. So that's 70. There's also timing since the chip select goes low, but since the chip select is constantly low, that doesn't affect us. Same goes for the output enable. It's constantly low, so that doesn't affect us. What about hold time? Actually, we haven't written that down. TDHR data read hold time 10 nanoseconds. So let's write that down. So we know the CPU needs 10 nanoseconds of hold time past the falling edge of the clock, which might have been a problem, except you will notice that it also promises to keep the address pass valid for 10 nanoseconds past the falling edge of the clock. So as far as the SRAM is concerned, nothing happens on the falling edge of the clock. Anything that happens only 10 nanoseconds afterwards. So obviously, if the data is valid here, it will also be valid here. It will remain valid so long as the address is valid. So hold time is not an issue for us. With that out of the way, let's talk about the write path. What we see is that the address becomes valid after 40 nanoseconds. And then after the rising edge of the clock, TMDS passes, which is write data delay time, 40 nanoseconds. So 40 nanoseconds after the rising edge of the clock, the write data begins to appear, which leaves us 62 minus 40, 22 nanoseconds to perform the write. Actually 32, because that's how long until the address line becomes invalid. Is that enough time? The write path also have multiple modes of operation. One is with the output enable being the clock, and we'll put that outside. The other is with the output enable low and fixed. That's our mode of operation right now. Let's see how that works. The address becomes valid, and then we have TWC, which is either 55 or 70 nanoseconds. So we're going with the 70 right now. So TWC is 70 nanoseconds. The chip select goes low and then goes high, except in our case, the chip select is constantly low, so that's not an issue. The write enable goes low, that's TWP. That's 50 nanoseconds. So the write enable goes low, and then the write enable goes high, and that has to happen within 50 nanoseconds. Are we fine with that? Well, the write goes low here and goes high here. So we have plenty of time. It goes low 40 nanoseconds after the falling edge of the clock, and it goes high 10 nanoseconds after the falling edge of the next clock. So we have clock minus 30 nanoseconds where it's not valid, and our clock is 125, so actually plenty of time. Last, we have the valid data. And the valid data needs to be TDW before the chip select or the write enable going high, and TDH after. TDW is 30 nanoseconds, and TDH is 0. Going back to the timing diagram for the CPU, we said we have 22 nanoseconds here and 10 nanoseconds here. That's 32 nanoseconds. That's enough time. But wait, we said that the TDH has to come after the write enable going high. Is that okay? And it seems that it is, right? Because we need 0 nanoseconds, and we see here that the read-write pin goes high after 32 nanoseconds. So it seems we're fine, except we're not. Let's look at TDH again. TDH is a minimum of 0 nanoseconds. So the data may become invalid as soon as the write enable goes high, but it may not become invalid before that. If we look at the datasheet for the CPU, we see TDHW, that's the amount of time after the clock that the data is guaranteed to be valid, and TAH, that's the amount of time after the clock that the address is guaranteed to remain valid. If we look at the datasheet again, however, TAH is a minimum of 10 nanoseconds, and TDHW is a minimum of 10 nanoseconds. In other words, This is not the amount of time that the data and the address remain valid. It's just the minimum amount of time. It may take longer, and the CPU makes no guarantee that the write data will remain valid up until the point that the read-write pin goes high. We actually have another problem. If we go back to this waveform, we see that one of the requirements we have here is that the address remains valid. We have TWR. TWR, a minimum of 0 nanoseconds, is the amount of time after the write enable going high that the address needs to remain valid. So again, 0 nanoseconds may not sound like a terrible constraint to have, but if we look at what the CPU promises, it bundles read-write with the address lines. In other words, it makes no guarantee at what order they will become invalid. If the address line becomes invalid before the read-write line goes high, then we might be writing to random addresses in memory. So in other words, despite the fact that this looks fine, it really isn't. Ben Eder noticed the same problem himself. This is the website for the 6502 on a breadboard project. And here are the schematics for the end result. Here's what Ben did to solve the problem. You will notice that the read-write line from the CPU is connected directly to the write enable pin of the 62256. So that doesn't change. However, you will notice that the chip select is connected not only to the A15 address line, which enables the RAM only when you're in the lower area of the addresses. So that is the effective chip select. It also uses this AND gate with the clock. In other words, the chip select is active, i.e. low, only when we're accessing the right address, but also only when the clock is high. The practical upshot of this is that if we look at this table again, the chip select is not constantly low anymore. The output enable is, but the chip select isn't. Instead, the chip select goes low when the CPU's clock goes high, and then comes back high when the CPU's clock goes low. In other words, the CPU will give us here 62 nanoseconds. How much time do we require? We need 60. So far, so good, but we need to check the other constraints as well. So, write enable is as before. We have it valid for pretty much the whole cycle. So write enable is not a problem. Time between write enable going low and the middle of the data valid, still not a problem because the write enable goes low pretty much infinitely in the past. Which leaves us with TDW. You will notice that we need the data to be valid 30 nanoseconds before the chip select goes high, which now actually is a problem. Remember, before we talked about the write enable going high, and we relied on the 10 nanoseconds hold time. Except now we no longer have the 10 nanoseconds hold time. The chip select will go high as at this point rather than at this point. So how much time do we have here? The write data becomes valid 40 nanoseconds after the rising edge of the clock, and the chip select goes high at the falling edge of the clock, which leaves us with 22 nanoseconds. What do? One thing we can do is switch to the faster version of the chip. So TDW is 30 nanoseconds in the -7 version of the chip, but only 25 nanoseconds in the -5. Which means that instead of missing 8 nanoseconds, we're only missing 3. And that might actually work. But before we switch, there's another problem that we've been ignoring. In fact, there's another problem that Ben Eater has been ignoring. Let's assume for the moment that we've got the right timing waveform covered. Like I said at the beginning, we're not really going to be running this at 8 megahertz. So be it 2 nanoseconds missing or 8 nanoseconds missing, we're probably not going to run into problems in our actual test harness. Our test harness will be running at a much lower clock speed. Instead, let's look at the read diagram again. So this is the read waveform we're using. And we used to have chip select tied low and output enabled tied low. Except we no longer have that. Instead, now chip select is only low during the high phase of the clock. Now, obviously, there are timing constraints here that we need to look at again, but that's not where I want to focus right now. Instead, I want us to have a look at the hold time requirement for reading the data. Remember, the CPU expects the data to remain valid for 10 nanoseconds past the falling edge of the clock. Before, we didn't have a problem because the address remained valid for 10 nanoseconds after the falling edge of the clock, so obviously the data remained valid as well. But that's no longer the case. Right now, as soon as the clock goes low, the chip select goes high, and then a certain amount of time later, the data becomes invalid. So we need to make sure that we have here the time between the chip select coming high and the data becoming invalid, that we have enough time to guarantee the 10 nanoseconds hold requirements that the CPU expects. Unfortunately, we don't have any line that anchors both here and here. We know how long the data is valid past the address becoming invalid. That's TOH. That's 5 nanoseconds. But we don't know how long the data is valid past the chip select becoming high. What we do know is that TCHZ, after the chip select going high, the output, D out, becomes high impedance. TCHZ is a maximum of 25 nanoseconds, which is more than enough, except it is also a minimum of 0 nanoseconds. So we have 0 to 25. And we know that by the time the data out is high impedance, it naturally isn't valid anymore. In other words, no, we do not have a guarantee on the 10 nanoseconds hold time that we need to supply the CPU. What's worse is that slowing down the clock will not solve this problem. It doesn't matter how long the chip select is low, which is how long the clock is high. As soon as the clock falls, maybe 0 nanoseconds later, data out is high impedance and the data is invalid. So no matter how slow phi2 is, hold time does not hold. No pun intended. The first thing we need to do is not tie the chip select to the clock anymore. So chip select goes back to be taken directly from A15. So just connect A15 directly to the chip select. So that's easy enough. But now we're back to the original problem, where during write the address fluctuates as the write might already be low, causing us to overwrite random areas in memory. But all we have to do is make sure that the write enable is tied to the clock. So instead of deciding that the chip select is tied to the clock, we need the write enable to be tied to the clock. This is slightly more complicated logic. Let's see what we need. So what do we have here? We have the CPU's read-write, and we have the clock. Those are our inputs. And as output, we have the memory's write enable. The easy case is if the read-write is 1. If the read-write is 1, which means we're reading, then we want the write enable to be 1, regardless of what the clock says. So that's easy. If the read-write is 0, then we want the write enable to be 0 only when the clock is high. So that's the truth table for the gate we're looking for. It's fairly easy to see that what we want is an OR gate saying we want 1 if our W is 1 or the clock is 0. So that's simple enough, except it's a bit of a bummer of a gate because it requires us 2 additional chips on the board. We need an OR gate and we need a NOT, an inverter. So that's a bit of a bummer, but De Morgan to the rescue. If you don't know, De Morgan means that an OR gate with both inputs negated is the same as an AND gate with the output negated. So if we apply this here, we negate both inputs, which means that we now have the clock going in directly and the read-write going in through an inverter, and we also need to invert the output. Now, seemingly I've only made it worse. Now I need an AND gate and 2 inverters, but actually that's not the case. First of all, AND plus a NOT, an inverter on the output, is already a gate called NAND. Better yet, NAND is implemented by a chip called 7400 with a couple of letters here. And we already have this chip on the board right here. It has 4 NAND gates, and you can see those in the design. Here it is. See? 74HC00. What about the inverter? Well, instead of using an inverter, we can just do an NAND gate where we tie both inputs. So we can just use 2 NAND gates to implement our gate. Great! Well, not so great. The 7400 has 4 NAND gates, and we're already using 3. Except we're not, because we're eliminating this NAND gate. Remember, instead of using this NAND gate, we're tying the A15 directly to the 62256 chip select. So now we have 2 free gates on the 74HC00, which we can use to implement the new gate and solve our problem. So let's look at our timing diagram again. Our chip select needs to be low for at least 60 nanoseconds. Since in our design the chip select is pretty much always low, we have it easily, not a problem. Next, we need write enable from low to high to be 50 nanoseconds. Our write enable is tied to the read-write line, which get update here until here, and the clock, the high level of the clock, which is 62 nanoseconds. So 50 nanoseconds, not a problem. Next, we need the data to be valid 30 nanoseconds before chip select goes high, or in other words, 30 nanoseconds before the clock goes low. That's a little more difficult. The entire segment is 62 nanoseconds, of which 40 the data is invalid. So that leaves us only 22 nanoseconds where the data is valid. So we are violating TDW. Just like before, we're going to just ignore this problem. We're missing 8 nanoseconds if we're using the -7 version of the chip and 25 nanoseconds if we're using the -5 version. And either way, our actual clock will be much, much slower than 8 megahertz. So that's not going to be an actual problem. Which leaves us with the hold time. Since the CPU promises to hold the data for 10 nanoseconds after the falling edge of the clock, and the write enable goes high with the falling edge of the clock, TDH is pretty assured. So our write path is pretty much covered. We're fine with the write path. What about our read path? Here things are even simpler. Since we just returned our read path to the very first one we analyzed, the one before we changed anything in the chip select, and we already saw that we can use the -7 chip here without violating the constraints, then the read path is fine as well. Remember, our chip select is low all the time, so we're using the address provided by the CPU to provide the hold time requirement. So there you have it. It's not every day I get to find the mistake one of my heroes did, but I hope he takes it with good spirits. I hope you find it useful. Thank you for watching.